Hi, and welcome everybody to the last example in this series. Today we're going to be building another sequential circuit, but we're going to be using D flip-flops. So let's look at the question. We're asked to build a sequential circuit that counts from 5 to 0 and takes a button X as input. Button X will be used to start the counter and reset the counter back to 5 during the countdown or when the counter finishes and has stopped at 0. So in our previous examples, we've only built a counter that just counts on its own. However, we're kind of adding a control element with this button X. First, we're going to be looking at our state transition diagram. Now, how many states do we have? Well, we're counting from 5 to 0. So we have 6 states. State 5, 4, 3, 2, 1, 0. If we're ready to transition from our present state to a next state, we need to assess what button X is. Well, let's consider if we're at state 5 and button X is 0. 5 is the beginning of the counter, and so we don't want the counter to start counting until button X is pressed. So if button X is 0, or rather X is equal to 0, then we stay at state 5. We don't move to state 4. However, if we are in state 5 and the button is pressed, then we will move to state 4. If we're in state 4 and the button is not pressed, then we will transition to the next state, which is state 3. However, if we're in state 4 and the button is pressed, then it will reset the counter back to 5. So if X is equal to 1 when we're in state 4, we'll go back to 5. And again, we'll wait in 5 until the button is pressed again. If we're in state 3, we see a similar pattern where we would transition if the button is not pressed to state 2. And if the button is pressed, then we transition back to state 5. We reset. We're going to be transitioning from 2 to 1 if the button is not pressed. And then we will transition from 2 to 5 where we will reset. Again, if X is equal to 1. And then finally we will move from 1 to 0, the end of our transition, if X is equal to 0. And similarly we will follow another pattern, the same pattern of resetting if X is equal to 1 again. However, in our last state, there's a few more things we need to consider. Now, if we're in state 0 and the button is pressed, what happens? Well, we're going to transition, we're going to reset. We're going to transition back to 5, so that's if the button is pressed. However, if we reach state 0 and the button is not pressed, well then we're going to be stopped at 0. So if the button is not pressed, X is essentially 0, then we remain in state 0. This is our state transition diagram for the counter that we want to build. So now again, let's think about how many flip-flops as we did in our previous example. Well, for this one we're using D flip-flops, but the number of flip-flops doesn't necessarily change. Let's consider our highest value, which is 5. And so how many bits do we need? Well, we know that 2 to the 3 minus 1 represents all the way up to the number 7. And 2 to the 2 minus 1 only represents up to the number 3. So we need to have 3 bits, which again, just as we saw in our previous example, is 3 flip-flops. However, we have more than just 3 inputs, or 3 bits as inputs, because although we have QA, QB, and QC as our outputs that become inputs from our flip-flops, we also have the input X. And so we will have 16 possible states when we build our state table. Okay, so now let's build our state table. Just as we did in our previous example, we're going to put the states in the very first column. Because we have 4 bits, we know that there are 16 different permutations that we need to consider as present states. As such, our present states will be X, QA, QB, and QC. We will see that for QA, QB, QC, we have these states 0, 1, 2, 3, 4, 5, 6, and 7. and we have all of those states again. What X does is it sort of says, okay, well, we have state 0 and we have state 0, but we have state 0 when X is not pressed. So for this example, when X is 0, we're in state 0 and the button is not pressed. For this example, we're in state 0 and the button is pressed. So these both can lead to different next states. If I fill in the rest of this table, drawing out all of the permutations, all of the possibilities, all 16 combinations of these 4 bits, so that the button could be pressed in any of these states, or the button could not be pressed in any of these states. It allows for us to cover all bases. For our next state, we're going to have our DA, DB, and DC. You might be wondering, why do we only have 3 bits? Well, because our counter, again, only counts from 5 to 0, so we only have a counter that is a 3-bit counter. X only serves as a control signal. That's why we have only 3 next state bits. So let's run through it and maybe it'll make a little bit more sense. So if we're in state 0, for example, and the button is not pressed, then we stay at state 0. If we're in state 1 and the button is not pressed, then we go to state 0. If we're in state 2, right here, and the button is not pressed, then we go to state 1. If we are in state 3 and the button is not pressed, then we transition to state 2. If we are in state 4 and the button is not pressed, then we transition to state 3. If we are in 5 and the button is not pressed, 0, the button is not pressed, then we remain in state 5. If we are in state 6, we don't care, because 6 and 7 we also do not care about, are states that we are not considering here. We do not care about 6 and 7. So I can also put these bits here. It doesn't matter how the button is pressed in 6 or 7, because at 6 and 7 we don't care about those states. For 0, when the button is pressed, if we're at 0 and the button is pressed, then we reset back to 5. So we go to 1, 0, 1, 1, 0, 1, which is 5. If we're in state 1 and the button is pressed, then we go up to 5. If we're in state 2 and the button is pressed, then we go to 5. If we're in state 3 and the button is pressed, again we go up to state 5. Made a mistake here. If we are in state 4 and the button is pressed, then again we go back to state 5. If we are in state 5 though, right here, and the button is pressed, X is equal to 1, then we go to state 4. So we go to 1, 0, 0. And we have just completed our state table. Now we're going to build our minimum sum of products using K-maps for each of these inputs, DA, DB, and DC. These are the inputs of our flip-flops. Unlike J, K, and T, there was no excitation table, so the next state is taken as is for the inputs of D. The D flip-flop, what it does essentially is Q just samples D on the clock edge, and so Q just becomes whatever D was. So Q is essentially sampling D every time the clock ticks. And so that is why our next state is essentially just the D. So for DA, we have X and QA. We have QB and QC. These are our bits in this configuration that set up this table, just as we have done in previous examples. So this will be the 2 rows where X is positive. These will be the 2 rows where QA is positive. This is the 2 columns. These are the 2 rows where QB is positive, and these are the 2 rows where QC is positive. We can use this again to better find our minimum sum of products. So if I fill in a table, just as we have in all of our previous examples, making sure to go in order. And let's just fill in all of our maps. Okay, so now I've filled in all the maps, and I encourage you to pause the video and to make sure that you've done it correctly as well and that you understand how we came to this point. Now we're going to find the minimum sum of products for each term. First, let's look at dA. For dA, we will have this implicant, and we will also have this implicant. So for this one, this would be QA and QC, or simply X. And let me denote which is which with the colors again. For dB, we have this implicant, as well as this implicant. So what are they? Well, for yellow, let's look at it. That would be QA. The two rows where QA is positive. That would also be where X is not positive. QC is not positive. And then if we look at the red, we can see that this is where X is not positive. In these two columns, we can also say it's where QB and QC lie. Let's look at DC. DC is a bit more complicated. For DC, we have this prime implicant, this one, and we can build one more to have our cover for DC. So first let's look at this yellow. This yellow would essentially be QB, QC not for yellow. Then I'll look at red. For red we have X naught, QA. And then I'll look at the blue. For blue we have X and QC not. And then for orange we have X. We have X and QA not. Now we're ready to build our sequential circuit.
Okay, so now that we've found a minimum sum of products for all of our D inputs for our 3 flip-flops, we can move on to constructing the circuit. Just as in our previous video, I've already constructed the circuit. It's obvious to see that we have, again, our clock input that runs to all of our flip-flops. Our circuitry, these are our minimum sum of products for DC, our minimum sum of products for DB, and our minimum sum of products for DA. I encourage you to pause the video and to double check that your minimum sum of products are the ones that are illustrated here in the circuit. We also have our input button X, which will allow us to use the circuit as it was intended. So if I begin the simulation and the clock begins to tick, you'll notice that the counter has actually finished already. We started when it was finished at state 0, and it is not going anywhere unless I press X. If I press X, then when the clock cycle goes high, the flip-flops update and the counter resets back to 5. If I press the button again, the counter will begin to count from 5 to 4 to 3 to 2 to 1 to 0, and it will stop at 0, just as we had intended. If I hold the button again and we go up to 5, if I press it again and we count down and I press it at 2 or 1, we reset back to 5. Notice that we never went down to 0, and that is because If we're ever counting down and we press the button, we want to be able to reset the counter back to 5. And also notice that the counter did not keep counting down. Okay, so our counter is working. That's always a good feeling. Give yourself a nice little pat on the back. This concludes our series on flip-flops and the examples on flip-flops. Thank you for joining us, and I hope you enjoyed it, and I hope you learned a lot. Thank you.